So this is going to be 100-1. We're going to be taking a look at exponential and logarithmic functions. Now, yesterday or last time we talked about exponential functions, and today what we're going to be doing is we're going to be examining the graphs and properties of those logarithmic functions. Now, to talk about logarithms, you probably have heard this term before in other math classes, but what exactly is that logarithm? Now, going back to those exponential functions, if I examine that exponential function of f of x equals b to the x, it actually passes that horizontal line test. So to draw like a brief sketch, it passes the horizontal line test. So if it passes the horizontal line test, I know it has an inverse. Now, the way that we describe that inverse, okay, we're going to call it a logarithmic function, or we use the word logs or log for short. And so by definition, the inverse of the exponential function, f of x equals b to the x, is called the base b logarithmic function, and is denoted by the inverse being log base b of x. So we read this as log base b of x. This base b will always be the inverse to this base here, referencing our exponential function. So if this base was 2, this would be 2. If this was a 3, this would be a 3. And so that's how they create those inverses. Now, if this said base 4, like 4 to the x, and this was base 3, granted, even though logs and exponents, the base of our exponent, has that quote-unquote inverse properties of each other, they're not direct inverses of each other. So just be aware of that. For them to be the direct inverses of each other, these have to be the same. Now, we're going to talk about a few notation when it comes to these. When my b is 10 or when my b is e, and what I mean by that is I'm referencing this b here in my exponential function, we can say that the common logarithm of a real number x is log base 10 of x, but we don't usually write it as log base 10 of x. We're just going to say log of x. So just know that log base 10 of x is the same as log of x. And that's the log that we see in our calculator. And so the log that's in our calculator is the same as log base 10. Likewise, the natural log of a real number, x, is log base e of x. Instead of saying log base e, we're going to use this word ln x, which is natural log. So just know that log base e is the same as this. And so if we want to use log base e, we're going to use that notation we have there inside of our calculator. Now, how do we get some of these properties of logs? Now, since we know that the inverse of an exponential function is a log, we can actually use what we know about inverses to determine these properties. So for example, we know that the inverses, you have to swap the x and y's or the domain and range. So that means that if my exponential function, if my domain is negative infinity to positive infinity, that means that for the log, my range is negative infinity to positive infinity. If my range is from 0 to infinity on an exponential, that means that my domain is from 0 to infinity. Now this is crucial, and we're going to examine this later, but that means with a log, we have domain restrictions. And we're going to talk about what those domain restrictions are in the future. But essentially, we can't have a negative number or 0. So they can't be negative, or it can't be 0. So that's something to kind of be aware of. Now the other thing is, if you remember, we have a horizontal asymptote at y equals 0. Well, if we're switching the x and y's, that means that we still have that asymptote, but now it becomes a vertical asymptote at x equals 0. So the x and y switched here. And so know with a logarithmic function, you actually also have that vertical asymptote. And these are just some of the properties. We're going to go later on to a slide that has more of the properties, but this is just kind of like a quick overview of all the different properties. Now what about the graphs? What does a log graph look like? Now, if I reflect both situations of b being greater than 1 and b being between 0 and 1 across the equation y equals x, which is what the inverse is, this is how we can actually model or create what our log function is going to look like. So this is y equals b to the x, and this is log base b of x. If my b is between 0 and 1, that's where we get that decreasing looking function. Well, if that gets reflected, right, that gets reflected this way, so we get that piece. This gets reflected this way, and that's how we get that piece. And so this picture here and this picture here are the basic pictures of what our log function is going to look like. Now notice, we have our horizontal asymptote at y equals 0. It's now become that vertical asymptote. Likewise here, we still have that horizontal asymptote, but now it's become that vertical asymptote. So here's a list of all the different properties, and I suggest that you guys go ahead and get these down. It just goes into some of the things we already talked about, like what the domain is, what the range is, the starting point. Okay, the starting point of all of our logs start at 1, 0 instead, so that's really, it's a good thing to know. It is 1 to 1, and they are continuous. We're going to talk a little bit more about this statement here. If I have this statement, b to some power a equals c, I can reread it as a log. So that base, I bring it over as the log of that base to the other side, so then log base b of c would equal a. We're going to talk about that a little bit more in our lesson, but just know that this is how we can switch between logarithmic equations and exponential equations. And then also, log base b of b, because those are inverses of each other, they cancel out. And b to the log base b power, because those are inverses of each other, those will also cancel out. And that's in terms of compositions of each other. Just know we're eventually going to talk about that as well. So I'm just bringing it up now, but we're going to talk about it and qualify it further. And so this is the shape when b is greater than 1. This is the shape when b is between 0 and 1 in terms of our base. So like if this was 2, 3, or 4, and if my base b was like 1/2, my mouse doesn't go that low. So anyways, but just know these are the shapes. We need to know what the shapes are. Here's the end behavior of what's going on with these. We need to know all that. So our first example, if we were to graph it, this is one of those things where something that we would want to do is we would want to enter these values in our calculator. So if I know this statement here, that log base b of b to the x, it cancels out and it's whatever my exponent is. Well, for this first one here, if I plug in 1, I get log base 5 of 1, which is the same as log base 5 of 5 to the 0 power. And so those cancel out and you get 0. For this one, I get log base 5 of 5. Well, this is 5 to the first power. Those cancel out and I get 1. And I can do the same thing if I have like 1/5. Well, I get log base 5 of 1/5. Well, this is going to be log base 5 of 5 to the negative first power. Those cancel out and you get -1. We're going to talk about that further, like how I simplified those things, but that's part of the logic here. And so going through that, I have all of those done here for us, so we can take a look at those. And then what you do is you just take those x and y's and you plot them on the graph. Okay. Now this is just one of those ways to do it. So like one of them, there's 1, 0, there's 5, 1. Okay, so we have all those. A few things to kind of mention here. Yes, these do follow our standard form, how things can shift horizontally and things can shift vertically. And we're going to talk about that at the very end of the lesson. So just remember, we can still shift things in standard form when it comes to logs. Now if we have ln, there's no way for us to exactly simplify ln correctly. It's just best to enter those values in the calculator. And so when you enter those in the calculator, here's 1, 0. At 0.5, we got -0.7. At 2, we got 0.7. If I plug in ln3, here's 3. We got like 1 point, it's about 1.1 right there. So just know that with ln, we have to enter those into our calculator. Now remember, when we're describing, like I just said, we're able to still translate things. We can still have the horizontal shift. We still have that vertical shift when it comes to logarithmic functions. Now the base, all that does is really affect how curvy it is. kind of like affects the horizontal and vertical stretching and all that different stuff. I just use log base a instead of log base b in this instance. It doesn't matter, it's just a variable. But just remember that this h, this affects our horizontal shift of our function. Our k affects the vertical shift of our function. Those still apply. So if I wanted to describe how does this function shift, I can say that this is going to move over horizontally 3 spaces. So what is that going to look like? Well, I know that my sketch, it starts at 1, 0, and my sketch, it's going to look something like that. Well, if it's going to horizontally shift over 3 spaces, that means that this is going to shift over 3 spaces. 1, 2, 3. Also, I have this vertical asymptote here. That's going to shift over 3 spaces. 1, 2, 3. So that's my new vertical asymptote. And then from there, I can go ahead and get my sketch. Now, if the question asks you to do a few more points, you're going to have to do a few more points for that. This one, ln of x minus 5 plus 2. Well, this one, I'm going to be shift over positive 5, and it's going to move up 2. So I'm going to horizontally shift 5 spaces and vertically shift up 2 spaces. So now, putting these on the number line, okay, if I wanted to visualize this, still, we're starting at 1, 0, and I do get that image. And then we still have that asymptote there. So there's my asymptote. And so now, trying to graph this shift, it's moving over 5 spaces. So 1, 2, 3, 4, 5, and up 2. My horizontal asymptote also shifts over 5 spaces. 1, 2, 3, 4, 5. And then I can go through and I can draw the image right there. And so that's just kind of like a brief sketch of how you can still translate these due to the horizontal and vertical movements. So what types of concepts were discussed today? We took a look at what logarithms were. How do we create a logarithm, like the relationship that it actually has between the exponential function. And so from feedback from you guys, what I want to know is what is the relationship between a log and an exponential function? And then also, what is the equivalent of log base 10 and log base e? So how would I write those? What is the equivalent of those? And go ahead and leave those in the comments. Now, as usual, if you guys do have any other questions with any other topics that I went over in the lesson, please leave them in the comments.